Hi, everybody. My name is Rosalie Connell. I'm a senior biomedical engineering major at the College of New Jersey. Over the past year, I've been observing and understanding better the systemic effects of radiation, specifically through quantifying femoral mechanical strength changes through two tests, three-point bending test, and femoral neck testing. The motivation behind this study is rooted in the fact that we really want to go to space. We want to colonize Mars, and we need to better understand how the human body reacts in a space environment. We have a really good understanding of the fact that space radiation causes detrimental effects to bone, specifically lowering bone mineral density or causing microstructural changes. However, we're not entirely sure how this relates to mechanical strength changes, and that's what my study aims to at least take a stab at. I want to start understanding that and hopefully contribute to the greater knowledge base of that topic. So the way in which I was able to study this was, like I mentioned earlier, through two mechanical tests, three-point bending test, which is displayed here, and femoral neck test, which is displayed directly underneath. For the three-point bending test, the load was applied anteriorly, posteriorly to a femur collected from a rat specimen, and this was completed until failure of the bone. Femoral neck tests were conducted with a custom fixture, also on the same machine that the three-point bending tests were conducted on, which was an Instron mechanical testing frame. And the reason behind the custom fixture for the femoral neck test was to mimic the acetabular cup or the hip joint, so that more appropriate or more accurate physiological loading could be simulated. Both tests were conducted, like I mentioned, until failure, and through these tests, force and deflection data were collected. So the graph that you see here and also here are force deflection graphs, and they were run through a custom MATLAB script that was able to obtain stiffness values, maximum load values, and energy to failure values. With this, we were able to run two-way ANOVA tests to understand the influence of dose of radiation and time point after radiation and how these factors contributed to overall changes in the three parameters I mentioned. This was conducted for each cohort independently. So for this study specifically, we looked at a helium-4 cohort, a protracted or long-term galactic cosmic radiation cohort or GCR cohort, and a short-term or acute GCR cohort as well. For significant changes, these were really only observed with respect to time and primarily limited to the helium-4 cohort. As you can see here, there are two graphs displaying stiffness changes, and these are significant ones for the helium-4 cohort. On the top, we have shaft stiffness changes, or the ones obtained from the three-point bending test, and on the bottom, we have femoral neck stiffness changes obtained from the femoral neck study. For the shaft stiffness, the significant difference that was found was between 7 and 180-day time period, and for the femoral neck stiffness, there was significance found between 180 and 7 days, 90 and 30, and 180 days and 30 days as well. The last significance that was found for this study was for the protracted GCR cohort for shaft stiffness, which is displayed right here. Based off the fact that the GCR cohorts have not been fully studied, we don't have the 180-day time period yet for this cohort. We believe that is part of the reason that there's not as much significance noted for this specific set. With that, helium-4 was the most mechanically strong within the three, so we think that the higher weight radiation will contribute more to mechanical strength changes. However, like I mentioned, without the 180 days, we're not exactly sure what the implications are for that. We do want to mention that previous studies have also supported this data that time point is the only influence on mechanical strength, not necessarily dose. We are working within a very low dose range, staying within the centigrade range rather than the gray range, which would become lethal to the animals. That could also explain why we're seeing limited amount of significant differences. But microindentation tests have also, like I said, confirmed these results, finding significant changes for time period, specifically within the 90-day time period on the microscale change. To further this data analysis and hopefully find more differences, we plan to pair cognitive data on a per specimen basis to determine which rats are most sensitive to radiation, or otherwise figure out which rats were susceptible to both cognitive and mechanical decline, and therefore separate them from the rest of the group and repeat statistical analysis on just this cohort that should have more radiation effects based off increased sensitivity to radiation. With that, obviously there's more work to be done, and I look forward to completing some of it. But this all could not have been done without the New Jersey Space Grant Consortium, so I just wanted to thank them for all their funding and support. And thank you all for watching. I hope you have a great day, and I look forward to continuing this work.